Okay, thank you. So I'll be talking about Bayesian Deep Learning. And pretty much almost all of the work discussed so far in the summer school has been focused on point estimation. So you're trying to train a neural net and find one set of weights that maybe solves a supervised learning task. It gets good accuracy on the test data. So why are we interested in Bayesian learning? And I like to think of it in terms of the 3 X's. So the first one is exploration. So let's say you have an agent that's trying to explore an environment and learn how to solve some task. And there's a kind of interesting setting, which is sparse reward reinforcement learning. So maybe the agent has to learn to execute a complex behavior before it gets any reward signal. And so in a setting like that, the best strategy is probably just to try to explore and seek out novelty. And so seeking out novelty, one way to solve that is with uncertainty estimation. So if you reach a state where you're very uncertain about the dynamics, then that's a good sign that you've found something new. And so, Bayesian learning can be used to solve some sparse reward RL tasks that are very hard to solve using traditional techniques. So we'll see some examples of Bayesian methods used for exploration. Another use of Bayesian learning is explanation. So if you have a data set that you'd like to analyze and figure out what was the underlying explanation of how this data was generated, you can often define a structured Bayesian model, and the components that you fit wind up being an interesting explanation of the data. So here we have an example of a time series data set that's broken down into multiple components. So maybe some long-term structure, some seasonal components, some seasonal structure with changing amplitude, and so on. And so this can give us some insight into the structure underlying the data. And another case where we care about Bayesian modeling is extrapolation. So a lot of what we do in machine learning is interpolation. So we have a new data point, and we've seen a number of data points that are very close to it, and we just have to kind of fill in the gaps. But if you have, let's say, a time series data set, and you'd like to make predictions that go well beyond the range of the observed data, then that's the extrapolation setting. And so doing extrapolation requires uncovering a lot more of the underlying structure. And so the agenda for this talk, so the title is Bayesian Deep Learning, but maybe a better description would be Bayesian learning with an emphasis on deep learning. And so a lot of the talk will be about the fundamentals of Bayesian modeling. So what does it mean to fit a Bayesian model in general? And I'll walk you through a series of models that gradually lead towards Bayesian neural nets. So we'll start with Bayesian linear regression, and then go to Gaussian processes, and finally Bayesian neural nets. And we'll also see some examples of how uncertainty can be useful. So we'll look at the example of calibration. So if your algorithm outputs probabilities, how do you know if these probabilities are actually meaningful? We'll look at examples of exploration, and then at the very end, we'll see how Bayesian learning can be applied to explainable models and to extrapolation. And I'm not going to follow exactly this order for the talk, so I'll kind of interleave the applications with the models. But this is basically the content that I'll try to get across. And so before moving to Bayesian models, I want to start with a fairly simple example of how probabilities can be important in deep learning. And that's the case of calibration. So you don't necessarily need Bayesian modeling to get calibration. It's one way to do it, but we'll see a different approach that works very well. So what do I mean by calibration? Well, the question is, if you have a network that outputs a probability distribution, right? So maybe you have a classifier that outputs a distribution over object categories. What does it mean if it predicts something with 90% probability? Well, you'd hope that if you ask the question 10 times and it gives 90% confidence each time, then it'll be right about 9 times out of 10. And so we can measure if this is true or not by looking at what are called reliability diagrams or calibration curves. And so what that means is the x-axis is the probability that the model attaches to some outcome, and the y-axis is if you take all of the instances where it assigns that probability, what's the fraction of the time that it's correct. And so these graphs are an example from Nate Silver's popular book, The Signal and the Noise, and they're looking at weather stations. So weather station will predict some probability that it'll rain tomorrow. And so you can measure, like, is this calibrated? If it says there's a 50% chance of rain, what are the chances that it actually rains? And so they looked at the National Weather Service, and it's, for the most part, it's pretty calibrated. So if it predicts 80% chance of rain, it actually rains 80% of the time. If it predicts a 40% chance of rain, it rains 40% of the time. Interestingly, the one case where it's not calibrated is if it predicts a 20% chance of rain, then the actual chance is more like 5%. And you can probably guess why this happens, right? If it tells you there's a 5% chance of rain and then it actually rains, you'll be really mad, right? You'll remember that. But if it predicts it's going to rain and it's actually sunny, then you don't really care. And, right? So the loss is asymmetric. And so I'll get back to that point later. And then they looked at local weather stations, and these are actually not very calibrated. And so they generally overestimate the probability that it'll rain throughout the entire range of the predictions. And so from the standpoint of predicting probability distributions, that's not so good. And so how does this apply to neural nets? So there's a very interesting paper by Grosse in 2017. The title is On the Calibration of Modern Neural Networks. And so they looked at a pretty wide variety of prediction problems, mostly classification problems, and they asked, are the networks calibrated? And so here is an example of the classic Linnet architecture. It's a ComNet from 1998, and if you train this on the CIFAR 100 data set, then there's a pretty broad range of the probabilities it assigns to the particular label. So this is the highest probability it assigns to a particular label. And it's actually pretty calibrated. And so when it predicts 60% probability, it'll be right approximately maybe 70% of the time. So there's some gap, but it's pretty close. But if you look at a modern neural net, so this is ResNet, basically state of the art at the time that they ran this experiment. If you look at the predictions on the validation set, it'll be predicting close to 100% probability most of the time. And its average confidence will be about 90%, so it's very confident, but the actual accuracy is about 70%. And so the probabilities aren't actually so meaningful. And if you look at the calibration plot, it's much less accurate than it thinks it is. And the predicted probabilities are only weakly correlated with the probability that it's actually correct. And so the model is not calibrated. And so how can we make it more calibrated? Well, let's say you have an algorithm that outputs a distribution over the targets, like the object categories, and it gets a loss based on the distribution that it predicts and the actual target. And so there's the notion of a proper scoring rule. So that is a loss function that has the property that the best thing the network can output is the actual probability of the particular target. And so the example of the weather stations involved something that's not a proper scoring rule, right? There's a very asymmetric loss. It gets a much higher loss if it predicts a low probability of rain and it actually rains than the other way around. And so it's not incentivized to output the correct probabilities. So in the case of neural nets, the canonical example of a proper scoring rule is the negative log likelihood, or cross entropy. Right? So that's the negative log probability that the network assigns to the correct target. And so if you train the network with this loss function, then it's incentivized to predict the right probabilities. But the catch is that there's a difference between predicting the probabilities on the training set versus the validation set. And so if you train a neural net, here's a very common thing that occurs. Right, so this is the errors on the test set. So the red shows the classification error. And over the course of training, that keeps going down. And so the longer you train the network, the better it gets. But if you measure the negative log likelihood, this is actually getting worse. Right? So the NLL is going consistently up. And the difference between the error and the NLL basically comes from the calibration. So the network is getting more accurate in terms of what fraction of the time is it correct, but it's getting worse calibrated because it's doing really well in the training set. And so it thinks it's really, really accurate. And it's getting much, much more confident. And that's causing the negative log likelihood score to get worse. And so this paper presented a very elegant solution to the problem. So they explored many different ways of calibrating a neural net. But the one that they found worked the best is actually something really simple, and that is temperature scaling. And so a classification network typically predicts the distribution using the softmax operator. Right? So that is defined in this way. Right? And I think you're all probably familiar with softmax by now. And the softmax is a function of these variables z, which are called the logits. Right? And the idea behind temperature scaling is that you just multiply the logits by some factor, probably something less than 1. Right? So instead of taking sigma of z, we take sigma of z divided by t, where t is the temperature parameter. So the larger the t is, the hotter the distribution is, the more spread out it is. And so there's basically one parameter, and they fit this parameter on the validation set. Right? And because they're fitting it on the validation set using negative log likelihood, it's a proper scoring metric, and so it's incentivized to make the predicted distributions more accurate. And so this actually, in many cases, basically solves the calibration problem. So here's the network before the temperature scaling. So if it were calibrated, then the predictions would basically line up with the diagonal line. After temperature scaling, it basically nails it. Right? So if it predicts a 40% probability, it'll be right 40% of the time. And so this is an example where there's a really simple method that's trivial to implement and very hard to beat. And that's a fairly common phenomenon in Bayesian deep learning. Yeah, question?
Just to have an idea, what's the temperature they fit it to? Like what's the value of t?
Oh, what's the actual value? I don't remember. All right, so let's see the first example of an actual Bayesian model. And this is actually the first example of Bayesian modeling. So this is based on the original paper by Thomas Bayes, an essay towards solving a problem in the doctrine of chances. And this example shows that back in the 1700s, you didn't have to do very much to get an entire subfield of statistics named after you. And the basic problem is you've observed a number of flips from a biased coin, and you'd like to infer the probability that it will come up heads. Right? And so if you've observed 2 flips and it came up heads both times, well, the maximum likelihood estimate might be that the probability of heads is 100%. But we know that's probably not the right answer. And so how can we approach this as a Bayesian modeling problem? So the idea behind Bayesian inference is that we treat the model parameters as a random variable. And I'll use the script D as a shorthand for all of the observed data, so all of the coin flips we've seen so far. And so in order to do Bayesian inference, we have to define 2 distributions. We have to choose a prior distribution, denoted P of theta, and that encodes our beliefs about the parameters before we observe anything. And we also have to define a likelihood function, written P of D given theta, and that defines the probability of the observations for a given value of theta. And so this is exactly the same as the likelihood function that you'd use in maximum likelihood estimation. And so there's really just one formula we need. So when we do Bayesian inference, we update our beliefs based on the observations, And that means that we compute what's called the posterior distribution. So this is the P of theta given D. And we compute that using Bayes' rule. And Bayes' rule just says that we multiply together the prior distribution with the likelihood, and then we normalize it so the whole thing integrates to 1. And the denominator of this equation is a fairly complicated integral. It's not always very easy to compute, but fortunately, we can usually ignore it. So in Bayesian inference, we rarely, if ever, compute the denominator. Instead, we can just use the proportionality notation. So the posterior distribution is proportional to the prior times the likelihood. And so for the coin flip example, the likelihood function is just the probability of all the observations. So what's the probability attached to the particular sequence of heads and tails that we observed? And the formula for that will just be the product of the probabilities of all of the individual observations, and that turns out to be the parameter theta raised to the number of heads times 1 minus theta raised to the number of tails. And so if we've observed a sequence of coin tosses, we might have a likelihood function that looks something like that. So that's the likelihood. The other half of the model is the prior distribution. So what do we believe about the parameters before we've observed any data? And so one way we can approach the choice of prior is to choose an uninformative prior, right? We'd like to assume as little as possible about the model. And so in this case, we might choose a uniform distribution over theta, right? So that's a fairly intuitive choice. But maybe we know something ahead of time, right? Maybe we know that the coin is more likely to have a parameter close to 50%. Maybe it's not exactly fair, but 50% is probably more likely than 100%. And so we might want to choose a distribution that encodes that. And there are a lot of choices we have for what family of distributions to use, but we can often choose it based on computational convenience. And so in the case of the coin flip example, a very convenient family of distributions is the family of beta distributions. So this distribution, it's a distribution over theta, and it's parameterized by two parameters, a and b, and it has this functional form. So it's theta raised to the a minus 1 power times 1 minus theta raised to the b minus 1 power. And there's a normalizing constant, which is kind of complicated, but I've grayed it out, which indicates that you can basically ignore it when you're thinking about Bayesian inference. And so depending on the values of a and b, you can get very different distributions. So if you choose a and b both equal to 1, you get the uniform distribution. That's the green line. If you choose a and b less than 1, then the distribution is actually concentrated near the endpoints. So it says that 0 and 1 are more likely than more intermediate probabilities. And if you choose larger values of a and b, then you get a distribution that's more concentrated towards intermediate values. And so we have a number of degrees of freedom in the choice of the prior. And so how do we compute the posterior distribution? Well, we just multiply together the prior and the likelihood function. And so if we plug in the values from the previous slides, then eventually we wind up with this particular expression. So we have theta raised to some power times 1 minus theta raised to some other power. And if you look closely at this, you'll notice that this is just a beta distribution, right? So we've multiplied together the prior and the likelihood, and then we've come up with a distribution that has a very convenient form. It's just a beta distribution. And so this happened because we chose the prior wisely, and in fact, we chose it based on a property called conjugacy. So conjugacy just means that the prior has the same functional form as the likelihood function, which means that when you multiply them together, then you'll get something that still has the same functional form. And so the parameters for the posterior, right, so the beta distribution parameters are a plus the number of heads and b plus the number of tails. And so for a conjugate prior, you can often interpret the prior hyperparameters in terms of pseudo-counts, right? So we're pretending that we already observed a heads and B tails. And so we're just, we're acting as if we had some extra observations. Yeah.
I'm wondering in practice how you determine the hyperparameter, because I guess in reality you probably won't do 4 base to infer the hyperparameter.
Right. So how do you infer the hyperparameters? And it really varies from one problem to another. Sometimes it doesn't matter too much. So regardless of the value that you choose, you might wind up with very similar predictions in the end. So we'll see an example of that in the next slide. Sometimes they do matter, but sometimes you have additional information that you can use to choose the hyperparameters. So maybe you haven't just seen one coin, maybe you've seen 10 different coins from the same source, right? So then you can pool the data from all these different coins and get better estimates of the hyperparameters. And so you can basically define a hierarchical Bayesian model where you put a distribution of the hyperparameters and then fit everything together as one big Bayesian model. Right. And so what happens when we do inference in this model? Yeah, question?
Can you comment on how the choice of the prior affects the sample complexity for doing inference?
Right, how does the choice of prior affect the sample complexity? So I think the most important way that the prior affects the sample complexity depends on the functional form of the prior. Right, so often there are very different kinds of models that you could choose for prior. So maybe if you have 10 different coins, you could assume that they're all independent under the prior. Right, so one coin tells you nothing about the next coin. But you might assume they're related, right? So maybe you somehow share prior structure between the different coins, and then having learned something about the first 9 coins will tell you something about the 10th, right? And so then if that's the correct model, then the information sharing can make it much easier to learn about the 10th coin. Yeah.
Can A and B be seen as pseudo-counts in the prior, or is it only seen as pseudo-counts when it's in the posterior?
So it's probably a matter of semantics. I mean, it's really just a matter of how the equations work out in the Bayesian inference. So I don't think there's really a formal definition of that. It's just a convenient way of thinking about it. Right. So how do the prior, the likelihood, and the posterior behave? Well, we can kind of distinguish the small data setting from the large data setting. So let's say we've observed 2 flips, both of them are heads, and we might assume a fairly broad prior, so one which assigns higher probability to 0.5 than it does to the endpoints, but still puts probability mass in a pretty wide range of hypotheses. And the likelihood function, well, because we've only observed heads, then the value that assigns highest likelihood to the observed data will be theta equals 1. So the likelihood function is monotonically increasing. And so when we multiply the two together, then we get the posterior distribution, and that will be essentially a compromise between the prior and the likelihood. And the 3 distributions aren't drawn to scale. I've normalized them arbitrarily so that they all show up in the same figure. So that's the small data setting. But now let's say that we've observed 100 coin flips. So we still have the same prior, but the likelihood function is much more peaked around a particular value. And so when we multiply these together, then the posterior distribution will also be very peaked around the same value, right? And so we say that the data overwhelm the prior, right? So the prior doesn't matter too much in this case. Our inferences will be dominated by the observations. Right, so that's a fairly simplistic model, but we can already do something fairly interesting with it. So I'll introduce the idea of Thompson sampling. Yep.
Is this true for any prior, or do we sometimes accidentally fix priors that we can't recover from using data?
Well, right, so it really depends on the task. Right, so this is kind of a simplistic example in that we're only trying to estimate one thing. What often happens is that you don't just have one estimation problem, but you have a lot of closely related estimation problems. So maybe if you're running an internet service, right, if you're Netflix, maybe you have some users who have rated thousands of movies and some users who have rated 1 or 2, And maybe you have just tons of data to accurately estimate the parameters for the really active users, and you can use that to somehow share information between different users and make predictions about the less active ones. And so that's where the prior information will become important. And so even if it's a very large data problem, there'll probably be some aspects to it which are essentially in the small data setting. Yeah.
Can you talk about how quickly this might happen in very high numbers?
Yeah, good question. So I don't know of a completely satisfactory answer to that, but so when we're training Bayesian neural nets, the dimension of the space will generally be larger than the number of training examples we have. And so in that case, we're definitely not in the setting where the data overwhelm the prior, right? The prior is still very important in that setting. All right, so the Thompson sampling is kind of an interesting example of how Bayesian methods can be used for exploration. And so the simplest example of this is probably the n-armed bandit problem. So this is something you'll be hearing a lot more about in the second half of the summer school when you talked about reinforcement learning. And this is a setting where you have n different slot machines in front of you, and each one of them pays off $1 with a different probability. And so you'd like to maximize the total payout over all of the trials. And this sort of requires managing a trade-off between exploration and exploitation. So you'd like to try the machines, try the arms that you believe are likely to be good, but you'd also like to sort of have diversity in your actions so that you can learn about all the other arms. And so you have to manage this exploration-exploitation trade-off. And so you can imagine some possible strategies to this, right? You could always choose the arm that you believe has the highest payoff. That's the greedy strategy. But this has the problem that you'll maybe get stuck doing the same thing over and over again and never learn about the other arms. You might try picking the arm whose parameter you're most uncertain about. But maybe there's an arm that you're sure is really bad, but you're not really confident about the exact value, and you'll keep trying that arm just because of the uncertainty. And so that's not really such a good strategy. So one of the common heuristics used in reinforcement learning is what's known as epsilon greedy. So 1 minus epsilon fraction of the time, you pick the greedy action, but epsilon fraction of the time, you pick a random action. And so you're mostly exploiting, but you're also doing a bit of exploration. And so so we'd like to basically manage the trade-off between exploration and exploitation. And so there's a very elegant algorithm for doing this called Thompson sampling. And this was actually introduced back in the 1930s, but it wasn't really used much in AI until the 1990s. And the idea here is that you fit a Bayesian model to the distribution. So in the case of the n-armed bandit problem, you have a separate Bernoulli parameter for each of the arms. And so it's exactly like the problem we just saw earlier, the fitting the parameter for a biased coin. And so you have a posterior distribution, and you just sample the parameters from the posterior, and then you act as if those parameters are the truth. Okay? So we can imagine that we have 3 arms. We have 2 arms that we've tried a lot, and we have highly concentrated estimates of their parameters. So one we're confident is close to 0.4, and one we're confident is close to 0.6. Then we have a 3rd arm that we haven't tried very much, and so we have a very broad posterior distribution over its parameters. So it's concentrated maybe around 0.3, but it's a very broad distribution. And so if we do Thompson sampling with this posterior, which arm do you think we're going to pick most of the time? Right? Who thinks we're going to pick the blue one? Yeah. Who thinks we're going to pick the green one? Right. So we're not going to pick the green one. How about the red one? Yeah. So most of the time we'll pick the blue one. Right? If we sample parameters from this distribution, we'll sample close to 0.6 most of the time for the blue arm. And the red one will typically sample values that are fairly small. And so when we maximize it, we'll wind up picking the blue arm. But occasionally we'll be very optimistic about the red arm, and we'll sample something that's closer to 0.8 or 0.9. And so then we'll take the argmax and pick the red arm. And so most of the time, we'll be picking the arm we think is likely to be good, but sometimes we'll be optimistic about the one we're uncertain about and wind up picking that. And so it's very convenient because it encourages exploration. So sometimes it's optimistic about things we're uncertain about, right? Optimism in the face of uncertainty. And it also, gradually shifts from exploration to exploitation. So as it learns more about the particular probabilities, the estimates become more concentrated, and the argmax shifts more and more towards the arms that are likely to have a high payoff. And so that's sort of intuitively the right behavior, right? Explore a lot early on, but then shift to exploitation near the end of the experiment. And so Thompson sampling is a very versatile idea. So I talked about the particular case of Bernoulli bandits, but we didn't really need much structure of the Bernoulli model, right? So all we have to do is we have to be able to sample from the posterior distribution, and we have to be able to take the argmax of the expected reward given what we sampled, right? And we can do that for a very wide variety of models. And there's a very interesting tutorial by Dan Russo, a tutorial on Thompson sampling, and they discuss very interesting and highly structured examples like stochastic shortest path problems, right? You want to find the shortest paths in the graph, but you only get to observe the edge weights. You need to get stochastic observations of the edge weights only for the parts of the graph that you visit, right? And so there's a fairly straightforward way to do this using Thompson sampling, and it's a very competitive solution to that problem. And there's a pretty interesting example of an RL algorithm inspired by Thompson sampling. And I just have basically one slide on RL here. I know some of you probably haven't seen much RL before, in which case you can tune out this slide. But this is a setting where we need to do deep exploration in order to learn about the environment. So we have n different states. We start at state S2, and there's a state S1 that has reward 1 over 1,000. And so it's very easy to find the state with a very modest reward. And there's another state Sn that has a reward of 1. And the agent can either move left or right. But the episode only lasts for n-1 time steps. And so if the agent consistently moves to the right, then it can find its way to the high reward state. But that requires consistently doing the same thing, right? So the problem is that if you use a heuristic like epsilon greedy exploration, then the agent will take a random action with some probability, but the probability that it happens to choose moving to the right consistently is very minuscule. And so for the agent to actually learn to act in this environment, it has to be able to consistently plan to reach regions that it's uncertain about. And so there was a very elegant algorithm inspired by Thompson sampling, which is the Bootstrap deep Q network. So the way that this works is it's DQN, except rather than just one Q network, it has an ensemble of networks. And in each episode, it chooses one member of the ensemble and then plans as if that member is correct. And so in each episode, it's using a consistent Q function. And so if the Q function believes that there's higher rewards to be found moving to the right, then it'll move consistently to the right. And so this algorithm is actually able to solve this toy problem, and it also performed well in the Atari benchmark environments. And so throughout this talk, I'll be giving very short summaries of a lot of recent papers, and so you can think of it just as sort of a starting point. So if you're interested in learning more about that, then you should follow up on some of these references. Okay, so any questions so far? All right, so let's move on to the next model, which is Bayesian linear regression. And so the way this works is it's just a Bayesian analog of linear regression, right? So we put a distribution over the weight vectors for a linear regression problem. And if we just sample from the prior, then we get a distribution over linear functions. If we have one observation, then, so let's say we observed this particular point, then we know what the value is here, and there are a lot of linear functions that are consistent with that. If we have a second observation, let's say right here, then we know a lot more about the function. And so we can be pretty sure that it looks something like these. And so how does this work mathematically? Well, we have to, for any Bayesian problem, we have to define a prior and a likelihood. And so the prior is also something, just like in the Bernoulli example, we have a lot of things we could choose for the prior, but we choose something that happens to be computationally convenient, and that is a Gaussian distribution. So we assume that the weights are sampled from a Gaussian distribution with mean 0 and some covariance. And if all you care about is computational convenience, there are a lot of different choices you could use for S, and there's some interesting ways to do that based on the theory of smoothing splines and things like that, but I won't get into those details now. So the prior distribution is a zero-centered Gaussian, and the likelihood is a Gaussian observation model. So you might have seen that linear regression can be seen as maximum likelihood estimation, where you have a Gaussian observation model. So we're just using the same thing for the likelihood for Bayesian linear regression. And so when we compute the posterior distribution, you just have to do a bit of linear algebra, and then you wind up with a particular expression. So because we had a conjugate prior, the posterior also winds up being a Gaussian distribution with a particular mean and a particular covariance. And the formulas wind up looking like this. So I'm not going to go through the formulas in detail. So I'm not going to focus much on the algebra in this lecture. But I think the one interesting thing to notice is that the formula for the mean, if you kind of move some symbols around, winds up looking very similar to the formula for linear regression in the non-Bayesian case. And so we can try to get some insight into how Bayesian inference behaves by looking at how the likelihood and the posterior change as we observe more data. So we might choose as the prior distribution a spherical Gaussian with a large covariance. So that's a very broad prior and puts probability mass over a lot of different linear functions. So let's say we observe one point. So the likelihood function for any one particular training example will basically constrain things along one dimension, right? So the log likelihood is a function of a linear function of W. So we basically constrain things along one dimension. And so when we combine the constraint from the first training example with a prior distribution, we get a posterior that's basically a compromise between those two. You can think of it sort of as the intersection of these two plots. So then when we observe one more training example, we constrain the values of the weights along one more dimension. And so then the posterior will be the intersection of the previous posterior with the new likelihood. And so now we've narrowed it down along 2 dimensions, and so we can actually pinpoint the value fairly tightly. And then as you observe more and more data, the posterior becomes more and more concentrated. And so now we have a posterior that's very concentrated near the correct value. We can make it a little bit fancier by, rather than making it linear in the inputs, we can use basis functions. So here's an example where we use radial basis functions or Gaussian basis functions. And when we draw samples from the prior, they look something like this, right? So we get very smooth functions. And the true function we're trying to estimate is the one shown in green, so it's a sinusoid. So if we observe 2 data points, then our posterior will be fairly concentrated close to these points. It will be very broad away from them. So we don't know much about the function value over here. And as we observe more and more data, then the posterior eventually becomes concentrated around the true function. So this is what we get when we've observed lots of data. right? So just like in the Bernoulli case, as you observe more and more data, the data start to overwhelm the prior. All right, so when we talked about the coin flip example, there's a very important detail that I glossed over, which is how do you actually use the posterior to make predictions? Right, so in the coin flip example, it was fairly intuitive roughly how you might do this, but in the case of Bayesian linear regression, we actually have to think about the details of how this works out. So the key object that we need for making the predictions is the posterior predictive distribution. So the posterior predictive distribution, P of t given x comma d, right? So remember, d is the shorthand for all of the observations we already have. X is the test location, and t is the function value at that point. Actually, it's the observation at that point. So it's the function value with noise added. And so the posterior predictive distribution will be essentially a weighted average of the predictions made by every possible weight vector, where the vectors are weighted by their posterior probability. Right? So it's the integral of the posterior probability of the weights given the observed data times the predictive distribution of t given those weights. And so we basically have to solve this integration problem. And fortunately, in the case of Bayesian linear regression, there's actually an analytical solution to this. So we can actually just solve this integral, and we wind up with a Gaussian distribution in the end. But if we don't want to predict a full distribution, and we're required to predict a value, then the way we do that is using Bayesian decision theory. So the idea is we use our posterior predictive distribution, and we pick a single value that minimizes the risk using our posterior predictive distribution. Right? We're trying to minimize the expectation of this loss function L of y comma t. And the value that minimizes the expected loss will be our prediction. That's y star. And so probably the most common example is if we use squared error loss. Right? So the value that minimizes the expected squared error will be the mean of the distribution. Right? So y star will just be the expectation of t given x and d. But a major advantage of Bayesian models is that we don't have to use squared error. We could use some other loss function. Right? So if you're doing something like medical diagnosis, you might have a very asymmetric loss. And so if you're doing Bayesian inference and you're careful to have calibrated outputs of the model, then you can do Bayesian decision theory and reason about what are the costs of different kinds of mistakes you can make and figure out the decision theory for what's the optimal thing to do in this case. And so if we've observed one data point, then we can look at the, so we can visualize the posterior predictive distribution in terms of the marginal means and variances at the different points, right? So what we're visualizing here is quantiles of the posterior predictive distribution. So we're visualizing the posterior mean and variance. And so the variance will be small, close to the points we've already observed, and it'll be large elsewhere. And so as we observe more and more data, then our posterior predictive distribution will gradually, so it won't converge to the correct function, right? So remember, our posterior over functions will eventually become concentrated around the correct function. Our posterior predictive distribution generally won't, because this distribution includes the noise that's added to the function values. Right? So even if we observe infinite data, the posterior predictive distribution will still have a fair amount of uncertainty, and that's because of the inherent noise in the data. Right, so I've gone through the example of Bayesian linear regression. It's not too hard to extend to the classification case. And I'm not going to go through the mathematical details of that, but let's say you have a logistic regression model, and you have two different sets of data. Maybe it's kind of hard to see on the slide, but you have one cluster of data here and another cluster of the opposite category here. And the colors visualize the probability assigned to the two different classes. Right? And for just a plain logistic regression model, there's this unfortunate property that if you're way out here, you're still making very confident predictions, even though you're far from the observed data. But if you fit a Bayesian logistic regression model, then it's not just fitting a single weight vector, but it's actually averaging the predictions over many different weight vectors that can explain the observed training data. And when you average over lots of vectors, then when you're far away from the data, you actually are much less confident. And so if you're here, maybe you believe it's part of this category, but you're not very sure. And so the predictions wind up being much smoother. So questions so far? Yeah.
Can you compare Bayesian linear regression to Gaussian process regression or some kind of regularized linear regression?
Yeah, so I'll talk about Gaussian processes in just a minute. And yeah, so you bring up ridge regression, right? So L2 regularized linear regression. And so that can be seen as doing map estimation in a Bayesian model, right? So rather than use the full posterior distribution, you just find the single most likely value of the parameters. So using a Gaussian prior and a Gaussian observation model, it's basically equivalent to the ridge regression optimization problem. And so it's often much more computationally convenient, but then you lose a lot of the useful properties of Bayesian inference, right? So a lot of the benefit of Bayesian inference comes from averaging over many plausible explanations of the data. Right, so in the case of Bayesian logistic regression, the high uncertainty here doesn't come from the prior, right? The high uncertainty comes from the fact that you're integrating over many possible explanations. And so that can often be really important to getting good predictions from a Bayesian model. Yeah.
So we know that from the point of view of generalization, the best thing you could do in terms of a linear classification would be the SVM or max margin classifier. But here we're averaging over a bunch of classifiers that are not necessarily the max margin one.
Mm-hmm.
Do we have to lose on generalization in order to get a confidence or robustness? Or?
I wouldn't say the max margin is necessarily the best thing to do, right? So you can derive generalization bounds in terms of the training loss and in terms of the margin, but those bounds aren't necessarily tight, right? So it's not necessarily the best thing you can do. Right, so you don't necessarily lose in terms of the generalization. In practice, Bayesian methods don't tend to be spectacular regularizers. And so if you compare the performance of Bayesian neural nets versus other things you can do like dropout, they tend to be fairly comparable. So the Bayesian methods don't kind of win spectacularly in terms of the test error. So it's a good regularizer, but there are other things you can do if you just need regularization. All right, so Gaussian processes. So I'm not going to go into a huge amount of detail about GPs. So I'm introducing these largely as some context for introducing Bayesian neural nets. But basically, GPs are kind of stochastic process, which roughly speaking is a distribution over functions. And they might be sort of hard to wrap your head around at first, but once you're used to them, I think they're actually a much more intuitive way of thinking about Bayesian regression. And so here is a sample from one particular Gaussian process model. And so the idea of defining a distribution over functions is, well, so Bayesian linear regression model already kind of does that, right? So we have a distribution over the weight vector W, and that defines a function in terms of W transpose times the feature vector, and W is sampled from a Gaussian distribution, right? So for any sample of W, that gives you a function, and so effectively we've defined a distribution over functions. And so if we let the vector f denote the vector of function values at some finite set of points, we can look at what is that distribution. And if you go through a bunch of linear algebra, you can show that this vector f has a Gaussian distribution with a particular mean and a particular covariance. And the formulas aren't particularly important for this lecture. What is important is that once we have this, then in principle, all of the computations underlying Bayesian linear regression are basically just conditioning and marginalization in a multivariate Gaussian. Right? So you just take all of the points corresponding to your training examples and test examples and anything else that you might consider relevant. You look at the Gaussian distribution over the function values of those points, and then you just do conditioning in a Gaussian distribution. And so that is another way of solving the Bayesian linear regression problem. So then the question is, why do we need to use these formulas, right? What happens if we just let mu and sigma be anything we want? And we have to put a few constraints on that, right? We can't let them be completely arbitrary. And so when I say let them be anything, what I really mean is that we can choose an arbitrary functional form for them. So what we have to define in particular is a mean function. Right? So the expectation of f is some function mu of x, and we have to define a covariance function. This gives the covariance between the function values at any 2 points. And so the constraint that we have to put on these functions is that for any set of points, we need a valid multivariate Gaussian distribution. And so we can define this matrix K sub x called the Gram matrix. That's the matrix whose value is the value of the covariance function between those 2 points. And so what we need is that for any set of points x that we choose, K sub x has to be a valid covariance matrix, which means it has to be symmetric and positive semi-definite. And so that is our requirement on x, right? For x, sorry, our requirement on k, right? For k to be a valid kernel function, for any set of points x we choose, K sub x has to be symmetric and it has to be positive semi-definite. But that's it, right? So we can choose any kernel we want subject to those constraints. And at the very end of the talk, I'll go through some interesting examples of kernel functions that we can define. And so basically, that's all we need to define a Gaussian process. So we have to define a mean function and a covariance kernel. And for any finite set of points, that'll define a multivariate Gaussian distribution. And the distributions at overlapping sets of points are consistent with each other because they're defined in terms of the same functions. And so there's a neat result called the Kolmogorov extension theorem. It basically says that if you have a whole bunch of distributions that are all consistent with each other, then you can extend them to a stochastic process. And so there's actually a distribution over functions, which you can think of as its own object. And so it's not really something we can compute with, right? Whenever we compute with Gaussian processes, we have to work with finite sets of points. But thinking about it as a distribution of functions gives a very intuitive way of thinking about Bayesian inference. Yep. I'm sorry? What does it mean for those constants? Right, so they have to be consistent with each other, right? So if we have 2 different sets of points and we look at the set of points they have in common, then the marginal distribution over those points has to match, regardless of whether we define the distribution over the first set or over the second set. And so we wind up with pictures that look basically like our Bayesian linear regression pictures, right? So we have some functions sampled from the prior for a particular GP kernel. And if we observe a particular set of points, then we wind up with a posterior distribution that has very low uncertainty close to the points we observed and high uncertainty away from them. Yeah.
What happens if the assumption about non-multivariate normal is violated?
Sorry, which assumption?
The points follow the multivariate Gaussian distribution. That assumption is violated.
Right, so if they're not right? So I guess what happens if we don't have a valid kernel matrix, right? So if k is not positive semi-definite at some set of points, then there's just no distribution defined for those points, right? In order to have a Gaussian distribution, you need a valid covariance matrix, and that has to be positive semi-definite. All right, so it's a Bayesian deep learning lecture. So finally we get to Bayesian deep learning. We're talking about Bayesian neural nets. And so we can define these basically analogously to all the Bayesian models we've defined previously. So we just have to define a prior distribution, and we have to define a likelihood function. So the prior on the weights of a network. So in the past, we've chosen priors based on conjugacy. Unfortunately, we can't use that trick for BNNs. There's really no prior we can define that gives us a convenient form for the posterior. And so we might as well just choose something simple like a Gaussian, right? So it's not completely satisfying, but it kind of works as a prior. And then we have to define an observation model. And so the observation model basically says that the distribution for the target at a particular point x will be a Gaussian centered at the outputs of the network with a particular variance sigma squared. So this would be a sensible likelihood function for a neural net regression problem. So then to do inference, we just apply Bayes' rule. And so conceptually, all we're doing is we're saying the posterior distribution of the weights of the network given the data is proportional to the prior times the likelihood. And if we make an IAD assumption over the data, that means the likelihood factorizes into a product of the likelihoods for the individual training examples. Yeah?
Why we ignore the covariance in practice?
I'm sorry?
Why we ignore the covariance for each data? I mean, for the...
Right, so in practice, you would typically use the different prior covariance for each layer of the network. And so these would be like hyperparameters that you would tune as part of the algorithm. Okay. And so BNNs were actually one of the first Bayesian models to be explored by the machine learning community. And so we can think of 1990 as roughly the time when Bayesian statistics really took off. People figured out how to do inference in really complicated Bayesian models. And so it really only took a few years for people to seriously look at Bayesian neural nets after that point. And so most of the important ideas can be found in two classic papers, or series of papers. There's a series of articles by David Mackay in Neural Computation in 1992, and then also Radford Neal's PhD thesis from 1995, Bayesian Learning for Neural Networks. And so we've probably made less progress over the last couple decades than we would hope. So probably the majority of the important ideas can be found in the very early works. The one thing that has changed since the 90s is variational inference. So we have variational algorithms for training Bayesian neural nets that closely resemble ways we would ordinarily train networks. So essentially things that look like variance of backprop, and they're very convenient ways of fitting large-scale BNNs. And so we can understand a Bayesian model by looking at prior samples of the functions. And so if we take prior samples of BNN, right, we sample the weights from a Gaussian distribution and then look at the function that the resulting network computes. Depending on the particular architecture of the network, we can get something fairly different. And so here we have BNNs with one hidden layer, and they're very wide networks, so they have 10,000 hidden units. If you use hard threshold activations, right, so it's a step function centered at 0, then you get very jagged functions, right? These are not differentiable. If you use a tan H activation function, then it's smooth, and the prior basically puts probability mass over much smoother functions. And so you can think about what sort of inferences the BNN would make just by thinking about how the priors behave and imagining doing posterior inference just like we saw on the slides for Bayesian linear regression. So unfortunately, inference in BNNs is much harder than inference in the tractable Bayesian models like linear regression. So we can, I guess, understand how BNNs behave by looking at infinite limits of the prior. So what happens if you take a one-layer network and let the number of hidden units grow to infinity? And in order to make this well-defined, you have to reduce the variance of the output layer in order to compensate for the number of hidden units. But if you do that, then Radford's 1995 thesis showed that under certain conditions, the limiting result of this is a Gaussian process. So for a wide enough network, BNN inference, so exact BNN inference, would basically closely resemble GP inference. Okay. And in recent years, it's been extended to more cases. So it's been extended to deep networks rather than just shallow ones. It's also been extended to convolutional networks. So it's closer to the sort of architectures we would actually use in practice. Unfortunately, you don't really get anything more interesting as you add more layers, right? So the limiting distribution for a deep network is a GP, just like it is for a shallow network. But on the other hand, this limiting argument isn't necessarily what we actually care about. So it loses a lot of why we're interested in neural nets, right? So you can actually show that in the limit of infinitely wide networks, it's not doing feature learning, right? So if you train an infinitely wide BNN and then try to use the representation for another task, it'll be just as if you used random initialization, right? So it hasn't learned anything that's going to transfer. And so this infinite width setting isn't necessarily the one that's interesting for deep learning. So unfortunately, inference in BNNs is much harder than inference in tractable Bayesian models. And probably the most common strategy we use is some sort of Monte Carlo estimation. So what we do is we sample parameter vectors from the posterior distribution, and we can only do this approximately. But if we have a sampled set of parameters, then we can approximate the posterior predictive distribution by averaging the predictive distributions for each of the posterior samples. And so if you want accurate predictions from a BNN, if you want accurate posterior samples, the way to do that is using Hamiltonian Monte Carlo. So that's a particular kind of Markov chain Monte Carlo algorithm, also invented by, introduced to machine learning by Radford Neal. And it's been over 2 decades, but this is still basically the gold standard for inference in Bayesian neural nets. And so if you're willing to wait a long time to get accurate results, this is what you would use. Unfortunately, HMC doesn't scale to large modern data sets because it's a batch algorithm. So every time you update the weights, you have to visit all of the training examples. And so there are a couple kind of quick and dirty approximations we can often get away with. So one of them is, rather than use a BNN at all, just use an ensemble of neural networks. So you have a bunch of networks trained on different random subsets of the data, and you estimate the amount of uncertainty in the predictions just based on the variance in the predictions for different members of the ensemble. And this works well for model-based reinforcement learning. So there are a couple recent papers that showed that model ensembles give more robust plans compared to single neural nets. And a closely related approach is Monte Carlo dropout. So a fair number of BNN application papers try to approximate posterior uncertainty using dropout, right? So dropout can be viewed as implicitly defining a large ensemble of neural nets. And so you can basically treat that as an ensemble for making the predictions and get a rough measure of uncertainty. So from a practical standpoint, if you want to train BNN at the large scale, probably the current way to do that would be with variational inference. So this is an approach which is less accurate than HMC, but more scalable because it's a stochastic algorithm. And so the idea behind variational inference is that we want to approximate the intractable posterior distribution with a much simpler and tractable one. Right? So the posterior over the weights of the network, given the observed data, would be some really complicated high-dimensional function. But we can approximate it with something simple, like independent Gaussians over the weights of the network. So each weight will have its own independent Gaussian distribution under the posterior. So I'll skip over the math for the interest of time. But basically, variational inference in general is maximizing a lower bound on the marginal likelihood. That's the probability of the data with all the parameters integrated out. And you can show that the particular lower bound is equivalent to minimizing the KL divergence of the approximating distribution to the true posterior distribution. And so you're trying to find the instance of the simple family that's as close as possible to the true posterior. And so the algorithms for doing this wind up looking very similar to ordinary backprop training of neural nets. So basically it looks like ordinary backprop training with noise added to the weights. So unfortunately, variational BNNs aren't such a good match to the true uncertainty, right? So here we have the predictions made by running HMC on a BNN, and these look very sensible given the observed data. If you run variational inference, then it kind of chokes on this simple toy example. And so if you're really interested in good uncertainty estimates, it's probably not what you want to be using. But there's another way of thinking about Bayesian inference that tells you where it's actually useful. And that is description length regularization. So when you fit a variational BNN, what you're really doing is you're regularizing the description length of the parameters of the network. And so the idea is that if this is your prior distribution shown in blue, and you have a very broad posterior, then it really only requires a few bits to encode the location of the high posterior probability mass, right? But if the posterior is much more concentrated, like here, then it requires a lot more bits to indicate exactly where the posterior mass is. And so when you try to minimize the KL divergence to the prior, that encourages the posterior distribution to expand. And so that will reduce the number of bits required to locate the posterior mass. And so the variational objective is really like regularizing the description length of the parameters. And there's a particular way of formalizing this, which I'm not going to go into, but it's called bits backcoding. And you can find a great video tutorial on this by Peter Beal, and it explains essentially how this can actually, how you can take a variational posterior and convert it into an actual code for the data that gets the number of bits that it theoretically ought to. And so this perspective of minimizing the description length has some interesting implications for BNN training. So one of them is for network compression. So let's say you want to run a network on a low-power device like a mobile phone. You want to reduce the memory usage for storing the network, and you want to reduce the number of computations required by the network. And so what you can try to do is you can try to prune the less useful connections. You can also try to quantize the weights. So rather than storing them as 32-bit floats, maybe you only need 8 bits to represent this particular weight. And so doing variational inference for a Bayesian neural net is one way of figuring out both which connections can be pruned and how many bits you require to model each weight. And so you can find this in a paper by Christos Louizos, and it really is well motivated by this description length interpretation of variational inference. And another instance where the description length view is relevant is in understanding the generalization of neural networks. So there's a classical result from pack learning theory that says if it requires only a small number of bits to describe your hypothesis, then you can show some generalization bounds in your model, right? If you get low training error and it requires only a small number of bits to describe your weights, then you'll probably get low test error as well. Right? And so the original results were for discrete hypothesis classes, but in recent years, so I think only 1 or 2 years ago, people were able to apply another kind of techniques called Bayesian learning. And they can take the description length interpretation of the variational objective and get analogous bounds on the generalization of neural nets. Right? So the KL term in the variational objective basically behaves like a description length bound as far as the generalization bounds are concerned. Right? And this is one of very few techniques we have to get non-vacuous generalization bounds for neural nets. Right? Almost any generalization bound, if you train a network on MNIST and then compute the generalization bound for the test data, it'll give you something larger than 1. Right? So it doesn't tell you anything about the generalization. And so this idea, this Bayesian analysis, which is very similar to variational BNNs, is one of the few ways we have of getting non-trivial generalization bounds for neural networks. So, questions so far? Yep.
Is it fair to say that BNNs are more data efficient than regular NNs? And if yes, then is it also computationally more efficient?
Right, so are they more data efficient? And so we can prove generalization bounds for variational BNNs that might be hard to prove for regular neural nets. In practice, they don't tend to be obviously better in terms of the generalization. So variational BNNs might generalize as well as dropout networks and things like that. So if you're just interested in maximizing the generalization performance, then you don't necessarily need to use a BNN. Mm-hmm. Yeah, these are pretty general. So there's not much structure that I assumed in defining the variational BNNs, right? So you basically just need a neural net architecture that you can do backprop on, and I think the variational BNN algorithms are pretty general. So you just do ordinary backprop, but with noise added to the weights. And so mechanistically, it'll work out. Now, whether or not the BNNs actually help in the application, well, that's really an empirical question. Yeah.
So I saw some work in the probabilistic programming community,
Mm-hmm.
which can define the distribution on the outputs and then they do posterior inference on the outputs, having a calculator. And this view is that you have a Bayesian distribution, you're performing a posterior on the parameters of the node.
Mm-hmm.
So how are these two different in terms of the use and application? And
Mm-hmm. Yeah, great question. Right. So I guess a probabilistic programming system will probably provide you with a very nice API where you can just define a model that looks like a distribution over the outputs, and it'll figure out how to do inference in it. I'm guessing that behind the scenes, it's probably doing inference over the weights of the network. It's just invisible to you as a user because it looks like maybe a Keras architecture or something. Behind the scenes, it's probably doing inference over the weights. We do have a recent paper called Functional Variational BNNs that directly tries to do inference over the functions computed by the network. So it tries to minimize a functional KL bound. That's fairly different from how BNNs are normally trained. And it's something that we're only beginning to figure out how to make scalable. But I'm guessing that a practical algorithm for BNN inference is probably doing inference over the weights behind the scenes.
So like one working which I saw was that they use neural network just for proposal distribution
Mhm.
and not doing any inference on the weights. So it's just like a fixed network, not Bayesian,
Mhm.
just for the proposal, and the actual Bayesian inference is happening on the data.
So they're doing some sort of importance sampling, or rejection sampling, or something like that? Yeah, sure, that would be one strategy. It probably won't work too well in the high dimensional parameter space. So maybe if it's a low dimensional problem and it's very likely that a prior sample will explain the data well, then yeah, rejection sampling might be the easiest way to do inference. But in a high dimensional space, I think the probability of a prior sample explaining the data well will just be infinitesimally small.
Is it prior or variation posterior to have an analytical form?
In general, no. So the prior will probably have to have some sort of analytical form because you need to be able to evaluate the prior log probabilities and the gradients in order to do inference in the model. But in general, the posterior will not have a tractable form. And so we have to do inference implicitly, either by approximately sampling from the posterior or fitting a variational approximation or something like that. The variational posterior should have a tractable form, right? So it's something that you want to be able to represent explicitly and optimize explicitly, but the exact posterior in general will not be tractable.
So, sorry, did you mean that Q here does not, does Q have an analytical form?
So Q is the variational posterior. That should be tractable, yes. Yep.
I didn't quite understand the relationship between description length and KL divergence. Like, do we need minimum bits to describe weights? But doesn't that mean that their distribution would be precise?
Right, so this is only a very rough intuition for why the KL divergence relates to the description length. Right, so on the left, we have a posterior distribution with a small KL divergence to the prior. And on the right, we have something with a large KL divergence. And it should be intuitive that it would require more bits to specify the location of this distribution than to specify that one. Right? But that's not a mathematical argument. And so in order to make it precise, you'd actually have to go to this bits back coding scheme that basically says that if you want to communicate the observed data, then what you can do is the sender communicates the weights of the network to high precision. Right? So the sender samples weights from the variation posterior, communicates those to high precision, and then the receiver can basically reconstruct all the data and then recover some of the random bits that were used to sample the weights. And so the sender can basically pack more information into those bits, right? So they could encode the data plus part of the text of War and Peace. And so because the sender can convey additional information, they don't have to be penalized for those bits. So basically, that's the gist of the bits back coding argument, which you can find in detail in this great lecture by Peter Beal. So the slides will be online, so you can follow all the links offline. Yeah.
Can you talk a little bit about applications where BNNs are involved from an applied perspective?
Mm-hmm. Yeah, so I think one of the most interesting applications is exploration. And I guess we're kind of out of time now, so I didn't get to talk about some of the exploration applications. But so Bayesian optimization is one case where you could use them. So Bayesian optimization is a way of doing black box optimization of functions that exploits the Bayesian model of the functions. And it's typically done with Gaussian processes, but BNNs have also been applied to it as a way of scaling to larger numbers of queries. There's been interesting work on intrinsically motivated RL using Bayesian neural nets. So you can essentially use the description length as a measure of how much the network has learned and use that as a reward function. And so as it increases the description length, it gets more reward. There's a really neat paper called Variational Information Maximizing Exploration that does that. So I think the link is somewhere in these slides. All right, well, I think that's it. So thank you.